Hi everybody, this is the last of our quick videos, so hopefully this has been helpful. Hopefully I haven't cut out too much of the information to be able to get the message across. I'm looking for your feedback, so please make sure you give it to me. Today's topic is a little bit longer, but I'm going to try to whip through it as fast as I can, and it's on something called free fall, which is actually a ride like Giant Drop for the Six Flags park that's in California, if I recall correctly. I know one of the Six Flags I've been to has a free fall, but it's like the Giant Drop. Um, so that should be your trigger, I hope, is the Giant Drop ride, because really, once the brakes let go, you're only being affected by gravitation. So you are falling, the car is falling, you're both falling at the same rate. And you might recall that that's actually being accelerated. So you get faster and faster and faster as you fall. And that acceleration for all objects, every single object, is this little g, which is a constant near the surface of the Earth. We say it's downward, so it's negative 9.81 meters per second per second. What does that mean? That means that every second that the object falls, it's moving 9.81 meters per second faster in the downward direction. And so check this out here. If I have an object here, let's say that's when I first start looking at it, and that's at time 0 seconds, and it just starts to fall, so it has a speed of 0 meters per second. I come back after 1 second and I say, hey, where's that object? How fast is it going now? So at this point now, how fast is it going should be easy, right? Because acceleration due to gravity is negative 9.81 meters per second for every second that it falls. If it's fallen for 1 second, then I know it must be going negative 9.81 meters per second. Easy, right? Now after 2 seconds, it's probably way down here, and so t equals 2 seconds. Here's my question, is how fast is it going? Well, every second, it increases its speed downward by 9.81 meters per second. So after it's fallen for 2 seconds, then we have a velocity now, I'm going to try to write it in there as best I can, of 19.62, and I don't care about sig figs, meters per second. And that's downward, so it's negative. So I could do that for as many seconds as I wanted to if it's in free fall. If it's not under ideal conditions, then all of a sudden this number starts to get smaller as the acceleration starts to get smaller, which means the velocity starts to get smaller, or starts to level off if it's moving fast enough. So we'll talk about that in just a minute. But it's all based on this idea of the gravitational field of the Earth. So here's what Newton said. Newton said that there's this field around the Earth, and if you're very far away from that field, you experience a tiny little bit of force towards the Earth. Just a tiny, tiny, tiny little bit of force getting pulled in towards the Earth. If you get even farther away, it gets tinier. Even farther away, it gets tinier, but technically it never reaches zero. It just gets so small that it could never be measured. I assume it could never be measured. But as you get closer and closer, look what happens. So this field begins to increase its strength as you get closer. And so let's say, so this is for an object that's here. What about an object that's here? Well, you're going to see it's got a much bigger force that's going inward. So now it's causing an acceleration that's higher as you get closer to the Earth, which is attracting it. As you get even closer, you're going to see a much, much bigger force. So now we've got the bigger forces coming in as you get closer and closer, which means you've got a bigger acceleration as you get closer to the surface of the Earth. At the surface of the Earth, the gravitational field this is about how strong it is. It produces this acceleration of negative 9.81 meters per second for every second that something falls. And it doesn't really matter what the thing is. The mass has nothing to do with it. Technically, the density has nothing to do with it. What does cause problems is the air resistance, and we can get rid of those air resistance problems if we assume that there's ideal conditions. So we have to try to figure out a situation in which air resistance will be minimized in our experimentation, and that will allow us to assume that this is a constant. I hope that makes sense. So let's use an example here. So the example is this. I have a rock, big rock, and it starts at a height of 100 meters above the ground. So some crazy person takes a rock 100 meters above the ground and then lets it go. And so my question for you is twofold, actually. How fast is it going right before it hits the ground? So v sub 2, how fast is it going right before it hits the ground? And how much time does it take to hit the ground? So those two questions we're going to try to answer here real quick. So how do we do that? Well, the first thing is we don't have time in this situation, right? We have no idea what the time would be because we're actually going to try to figure it out. So you have to pick which one of these you're going to go ahead and try to do first. If you try to pick time first, it makes things a little bit trickier, but you can still do it. So let's take a look at how we would do that. So let's assume we have the initial velocity, we have the displacement that it's going to have, and remember it's from here down, so this will be a negative displacement. So that's a delta y technically, right? And we're looking for the time. We also know one other thing. It's falling, right? So you can't ever forget that you have that as a constant for things that are in free fall. So we know a displacement, and we know an initial velocity, and we know an acceleration, and we're looking for time. If you haven't already figured it out, the best place to go is that master motion equation, which we talked about in one of the last videos. It says this, delta y, because we're doing a vertical displacement, is equal to v sub 1 times t plus 1/2 little g, because our acceleration is due to gravity, times t squared. Now we don't know the t's, and we're going to be able to find that out from this formula. The reason why we're going to be able to find it out pretty easily from this formula is this guy right here. So I chose that specifically to make your life easier in this case. And most of our experimentation, we have a zero initial velocity. So what happens to this term right here? If the velocity is zero initially, well, it goes away. So I can ignore that. And so I end up with just this, delta y equals 1/2 g t squared. Again, I'm trying to solve it for t. So I bring the 1/2 over by multiplying both sides by 2. I bring the g over by dividing both sides by g, and then I take the square root, and I end up with t equals the square root of 2 delta y over g. And so I can figure that out fairly quickly, I hope. I'm going to have to do the math on my calculator, though, so it is what it is. So 2 times 100 divided by 9.81, and then take the square root, gives us a time right here of 4, I think we have 4 sig figs, sorry, 4.515 seconds. So I know exactly how long it's going to take to fall. Then my next question is, how can I figure out how fast it's going? Well, because I want to help you to practice this a little bit, I'm going to ask if you could use the no time formula. I know you just found the time. But quite honestly, if you are in a situation where you're trying to find things like the time and the speed, you shouldn't really, if you have a choice, use the time back in the equation to try to figure out what the speed is, because you may have done the time wrong, and so you're sort of betting on the fact that your speed is going to be correct even though you're not sure that your time is right. So much better to only use the equation information that's given to you in the problem. So let's pretend we don't have the time for a second here. So no time. So which formula do we use? We use the no time motion equation, which is the second one that you learned. It says this, v2 squared, equals v1 squared plus 2a, but our acceleration is g in this case, and then delta y. Okay. And so my question for you is this, how can I solve this to be solved for the final speed? So this I know goes away because it's 0 right there. And then I know I have g, and I know I have delta y, and I know the negatives are going to cancel each other out just like they did over here. And so I have to take the square root of both sides, and so I end up with v sub 2, square root of v sub 2 squared equals the square root of 2g delta y. So I'm okay because this is a negative 9.81 and this is a negative 100, so those negatives are going to cancel. So I end up with v sub 2 equals the square root of 2g delta y, and then I can go ahead and do the math again. So 2 times 100 times 9.81 equals that, and then square root. So I end up with a v sub 2. That's 44.29 meters per second. I think I have 4 sig figs still. And then the direction is negative, right? So it's downward, so that should make sense. So I go ahead and put that on there. This is really asking about the final speed. So if I want a final velocity, I would add the negative sign on there, and that should make sense. So that's how we use it. Hopefully that makes sense. If you have any questions on how to use it, or how to talk about free fall, or whether or not this is actually constant for all sorts of different objects, we're going to do a lab on that, so that hopefully that'll help. Okay, let me know if you have any questions.